Welcome to my channel, A Woman in Physics. Yesterday I've been helping one of the neighbor's kids with his mathematics homework. He's supposed to learn about the importance of pi. And no, I'm not talking about this sweet delicious stuff that you can eat and that I really like from time to time. No, I'm talking about this constant pi. You know, he's supposed to learn where it comes from and where you have to use it and how to calculate it. And when we were at the point of talking about how can we actually calculate pi, it started to rain outside. You know, not heavy rain, but droplets started to fall, and I wondered, why not go outside and use the rain to calculate pi? So let's go! How can we now actually calculate pi? In a first step, let's take a circle. We know this circle has a certain radius r. And we know, of course, that the area of this circle equals pi times r squared. Now in a second step, let's put a square around the circle. Then we know that the edge length of this square equals to the diameter of the circle, which is 2 times r. And we know that we can calculate the area of the square relatively easy. It's the edge length squared. But if we have this, we see already that we have two equations. In only one of them we have our pi that we want to calculate. So we can take both equations and divide the first equation by the second one, left side and right side. And what we get is that the area of the circle divided by the area of the square equals pi divided by 4. So if we could measure the areas, we could actually derive pi relatively easy. But this is exactly where our problem starts, because we cannot just measure the area of the circle. Hence, we have to make an approximation. And in order to make this approximation, the rain that I mentioned earlier comes into the game. Because what we are going to do is we admit that we cannot measure those two areas, but we can count the number of droplets that hit our surface. And we just say, okay, I cannot actually measure both areas, but let's estimate the relation between the area of the circle versus area of the square by the number of raindrops that hit the circle and the square. And if we can do this, then we could actually calculate pi relatively easy. And we would expect pi to be something like 3.14159 and so on. But does this actually work? So what we did is we took a couple of images from the back porch as the rain started to set in. And we took one of the images and put it in a graphics program and put a circle and a square somewhere randomly. We didn't, choose this part in purpose. We just said, okay, let's put it somewhere, anywhere. And then we started to count the raindrops that had hit circle and square. Now, of course, the number of rain droplets within the circle is always smaller than the number of droplets hitting the total area of the square. And if we actually count them, we get that the number of droplets within the circle equals 21 and the total number within the square was 25. And if we put those two numbers now in our equation, we can calculate pi as 3.36. Well, yes, this is not exactly pi. I have to admit this. But I suppose it's not that far off if you think about it. Pi equals 3.14. so it's not that bad. At least we didn't get something like 0 point anything or something closer to 4. So it's not that bad. So how can we get better? And the neighbor's kid got the idea that let's make our square and circle bigger. Let's count more. Okay, we doubled the size. We started to count again, and we found that now in the circle we had 88 droplets and in the square we had 111 droplets. If we put those numbers again into our equation, we get 3.17, which is definitively closer to 3.14, our expected value. So good for us. But for actual mathematical calculations, this is still not good enough. So in the last step, we doubled the size again and started counting again. Now this took quite some time, and we got that the number of droplets in the circle was 318 and in total in the square 405. And if we put it back again into our equation, we get pi as 3.14074, which is not that bad, I have to admit. And it gives us an idea of what we have to do in order to actually get good values for pi, an accurate value for pi, or at least as accurate as we may need it. Because if we have one final look at this equation that is shown here, 4 times the number of points in the circle divided by the number of points in the square, we already see that, of course, I cannot just work with 1 or 2 points, because if I work with 1 point only, this point is either within the circle or outside. So pi would be, if it's within the circle, equal to 4, and if it's on the outside, just in the square, pi would be equal to 0, according to this equation. But as you've just seen, taking more and more points into consideration gives us more accurate values. And this is precisely what you could do. For example, if you're able to program, just write a small program. Use some random numbers and have your computer generate quite a large number of them. And you will notice that when you take not 10 random numbers, not 100, but 1,000, 10,000, let's go to 1,000,000 random numbers, then you will realize that pi gets more and more accurate. And this is a pretty neat way to actually calculate this number, pretty precise. But you have to be careful that you take actual random numbers. Of course, you don't have to take rain droplets to calculate it. But think about it, are there other ways that you can, generate random numbers? For example, using maybe dart, a dart game. And you try to hit your circle and a square that you have to make around it randomly somewhere. It should also be working, or would it work? Let me know in the comments below. And with this thought of let's find new ways to calculate pi, I'll leave you for today. Thanks for watching and see you soon. Bye!